So let's look at an example of writing the partial fraction decomposition. We have a fraction here, x plus 2 over x cubed minus 2x squared plus x. This is the answer. So we have to write the question. So the first thing we got to do is factor the denominator. So I see an x in every term, so I'll take out an x as the GCF. And then I have x squared minus 2x plus 1, which factors to x minus 1, x minus 1. And therefore, these two binomials will be written as x minus 1 to the second power. So we're going to write a fraction for each factor. The factors are all linear. Even though this is raised to the power of 2, it's on the inside as a linear factor, x to the first power. And this x out front is another factor. So our fraction is going to equal capital A over x plus capital B over the x minus 1 binomial to the first power, and then plus capital C over x minus 1 binomial squared. Again, this is a linear factor. Okay, so think about this. If we had to add these fractions together, we need a common denominator, and we would have to adjust all your numerators to add and combine all like terms, and you end up with x plus 2. So that's what we're going to do. Every denominator needs to have the LCD, and the best part, it's your factored out denominator. All right, so looking at this first x, it needs the binomial x minus 1 squared. And I multiply that to the top and the bottom. The binomial x minus 1 in the second fraction needs this x and another binomial. So I multiplied the top by x and the binomial x minus 1, and on the bottom I multiplied it to get my LCD. And my third fraction, I have the x minus 1 squared. I just need to multiply the x to the top and the bottom. So I did, and you'll see there's capital CX. So again, first fraction needed the binomial squared, multiply top and bottom. There it is. Second fraction needed the x and another x minus 1. And the third fraction needed just an x. So what we need to do is multiply out the tops. Okay, now when we do this, we're going to work smarter, not harder. Don't foil this. You already have it up here in the factoring process. So your x minus 1 times x minus 1 is x squared minus 2x plus 1. Distribute the capital A to each of those terms in the trinomial. That's the ax squared minus 2ax plus 1a. Here, we'll just distribute the capital Bx to the x, get plus capital Bx squared, and a minus capital Bx, and no change to our capital Cx. Now, since all the denominators are the same, I don't need to write them down anymore. I just need to focus on what do I need to have for capital A, capital B, capital C, so I can write these three individual fractions out. All right, now, the way I like to do this, because it works for every single form of the problem that you can ever encounter, even if you make a seriously huge, difficult system of equations to solve, because you can have your calculator do an RREF in matrix form, and you're done. Okay, and to do that is you're going to do a collection of all your like terms. So I have an x squared here and an x squared here. But notice that if I add ax squared plus bx squared, there is no x squared over here. So I'm going to put in a 0x squared. What that tells me for my x squared terms, that the a plus the b have to add together to be zeros, which means a and b have to be opposites of each other. That's okay. All right, my next terms I'm going to collect are my x to the first power. So here's an x to the first. That's a 1. I have a minus 2 capital AX, and I have a minus BX and a plus CX. So dropping the x's, you have 1 is equal to negative 2 capital A minus capital B plus capital C. You can see my system of equations starting to develop. I'll later put the 0 on the right and the 1 on the right. And if I have to go to my calculator, I'll do a RREF to a 3x4 matrix like we did in earlier videos. And last but not least, we're going to collect the constant. Positive 2 is equal to, oh, we only have one A. Okay, wait a minute. So A is equal to 2. We're good. Whoops, come back here. We can do some back substitution now. We can put this 2 in for this A up here and solve for B. Well, remember we said A and B are going to have to be opposite, so B is equal to negative 2 to make that a true statement. Well, now that I know A and B, I can plug them into the second equation and solve for C. So 1 equals negative 2 times positive 2 for the A minus the negative 2 for the B plus C. So that's negative 4, that's going to be a plus 2, so that's negative 2 added over to the other side, and C is equal to 3. So we'll substitute in our answers for A, B, and C back at our beginning statement right here. So our partial fraction decomposition is A, 2 over x, plus our B, negative 2 over the x minus 1, plus our C, which was 3, so plus 3 over the x minus 1 squared. And if you want, you can double check this with your calculator to make sure it's working. So I went to my calculator, and for giggles, I just put in 3 for x. I stored it. Just make sure that you don't choose 0, because that makes this fraction undefined, or a 1. That'll make these two fractions undefined. So I typed in the original problem, and it said it was 5/12. I typed in my answer, my partial fraction decomposition, and it gave me 5/12. If you have an older calculator, here's my screenshot. I put 2 in for x this time, and that's this 2. Kind of fell off my screen. The downside is now with the older calculator, if you don't have that alpha y equals for your fraction shortcut screen, you have to put parentheses around the numerator over parentheses around the denominator. And I did that, and I got a 2. And then I went 2 over x plus negative 2 over x minus 1. 2 items in the denominator. You have to put parentheses. And the same for the second fraction. And this also came out to be a 2. Now, your author is going to use what is called a modified zero product rule. I'm not a fan of this because it doesn't work all the time. It's quick and easy. It looks good until you run into some problems with canceling out some binomial factors. So what the author says is don't multiply it out. Oh, check this out. Let's let x equal 0. So if x were to be 0, this cancels out. So c times 0 is 0. B times 0, oh, this is all going to cancel out. So you're going to put a 0 in for this x. That's the 0 plus 2. A times 0 minus 1, which is negative 1, squared, which is 1. Look how quick and easy that was. A is equal to 2. All right, let's cancel out the 1 binomial, x minus 1. So let's let x equal 1. All right, this binomial cancels. This binomial cancels. So this is a 0, this is a 0, so we'll put a 1 in for this x, a 1 in for that x, and oh, look how quick and easy that was. 1 plus 2 is 3, c is equal to 3. Okay, how do you solve for b? You can't cancel these two out here without canceling this out. And that's what I don't like. So the author says, well, let x equal some other number, and we'll fill everything in for the x's, the a, and the c, and the b will be left, and then we'll just solve it. Okay, so here's how crazy it gets. This 2 goes in for x. This 2 goes in for this x. This 2 goes in for these two x's. This 2 goes in for the x. There it is. All right, simplify all that. Crunch, 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 crunch. Okay, 4 equals an A plus 2B plus 2C. Oh, that's right. A was 2. Bring that down for the A. C was 3. Bring that down for the C. So 2 plus 6 is 8. Subtract over the 8. Gives you a -4. Divide by 2. B is equal to -2. Okay, it's quick up front, but then it could possibly be a lot of number crunching. Okay? It's valid. It works, but not all the time. All right, so that's my linear factor example.